Okay, guys, I think we can start now. Um, um, so today we're gonna uh, talk about matrices. So this will be lecture. This is lecture 3, and there are a lot of things to talk about here. Okay, so here we go. So lecture 3, matrices. And here, probably as you have already seen in my notes, there are a bunch of things that I want to cover. And what are we going to discuss in this 1 hour and 20 minutes, or maybe a bit more? We'll talk about matrices, what is a matrix, about the algebra of matrices, when can we add two matrices, when we can multiply two matrices, about the inverse of a matrix. Then we go back to systems of linear equations, how to solve systems of linear equations using matrices language. Then we'll talk about a special type of matrices, which we'll call the elementary matrices. And then if time will allow, maybe I'll talk about a bit about the LU factorization. Well, to be honest with you, I don't like how LU factorization is presented in the notes and therefore in the book and therefore in the notes. So it will also involve some kind of determinants. So probably when I will talk next week about determinants, I'll also go back to LU factorization as well. Okay, so now let me start. So a matrix. So what is a matrix? So a matrix is something that looks a little bit like this. So let me denote A. It's a matrix, so it has the entries Aij with I between 1 and m, and j is between 1 and n. And this will be, we'll have the entries A11, A12, A1n. Then the second row will be A21, A22, A2n, and we go all the way to AM1, AM2, AMN. So this is, as you can see, this is how a matrix would look like. As you can see here, this is what we'll call row 1, the first row. This will be the second row, and this will be the row M. And these guys here, this will be column 1. This is column 2. And all the way, this is column N. So we call this a matrix of size. So this is A, is a matrix of size M by N. This means that M rows and N columns. That's what it means to be a matrix. So this is how we write the matrix. And as you can see, we can also have the number of rows doesn't necessarily has to be equal with the number of columns. So when the number of rows is equal with the number of columns, in other words, when m equals n, then we say that the matrix A is a square matrix. Matrix A is a square matrix. That's what it is. And for example, they're let me give you an example of matrices. Example. Let me take the first one, A to B. Well, let me take a 2, 3, 3, 1. This is a 2 by 2 matrix. 2 by 2 matrix. It's a square matrix. Another example is, let me take a matrix B of the following: 2, 3, 5, 6, 7, 8. So this is, it will be what? 2 by 3 matrix. So this is not a square matrix. By the way, somebody is typing. Can you mute yourself? Who is that person? Yeah, somebody is typing, I think, and has his microphone on. And okay. Who is? Okay. Somebody's typing. Ibrahima, is that you? Okay, probably, yeah, because okay. All right. So these are the two examples. So the first one is a square matrix, and the second one is not a square matrix. Let me give you another example of a matrix. Let's say C. This will be, let me take 3, 0, 5, 4, 1, -1, and 1, 1, 2. This is again a 3 by 3 square matrix. Okay, so probably now you would like to see what kind, so the question we want to answer, what kind of operations can we perform with matrices? With matrices. And here, of course, when I talk about operations, I have in mind addition, scalar multiplication, subtraction, if you want, and why not matrix multiplication and multiplication. By the way, there will be a distinguish between scalar multiplication and multiplication of matrices. All right, so let's talk about the first three, and then we'll leave a little bit after the matrix multiplication. So the first, so matrix addition. So we'll want to talk about matrix addition, subtraction, and scalar multiplication. Okay. So these are the three operations that I want to talk about in the first place. So let me start with a definition. So as you may imagine, and just like I explained in the first lecture when we talked about what a matrix is and so on a little bit, let's talk about how to add two matrices. So matrix addition. So if I have a matrix A and the entries of this matrix are IAJ, and B is another matrix and the entries are BIJ, right? Our matrices are of size, and this is very important, m by n, right? I do not consider them to be square matrices, but I do consider them to be of the same size. And then there are some is the m by n matrix. Let's call it A plus B, which the entries for this matrix A plus B will be nothing else, as you can expect, Aij plus Bij. So, and now, well, I said it here clearly that the two matrices must be of the same size. So the sum, let me point out the remark here, the sum of two matrices of different sizes is undefined. Of different sizes is undefined. So, like I said, only when you can add two matrices only if they're of the same size. I don't want to. Well, let me give you a quick example. If you add, let's say, two matrices, 2, 1, 0, 3, and let me B to B. Of course, I have to take a. This is a 2 by 2. I will have to consider another 2 by 2, 0, 1, 2, 0. So as you can expect, A plus B will be nothing else than just, let's write them again so that you can see it clearly. So I will add these elements. So the first element so this is on the first element in the first row with the first element in the first row of the second matrix. So we'll have 2 plus 0, 1 plus 1, 0 plus 2, and 3 plus 0, which will give us again a 2 by 2 matrix, which will be 2, 2, 2, 3. So see it 2 by 2. And this is how you add for all matrices of all sizes. So, okay. So this is how you add two matrices. That's very, very simple. And now let me give you another quick definition of scalar multiplication. So I mean here scalar multiplication. So a scalar multiplication, so if a matrix, if A, let's say this is a matrix A with the entries Aij, is an m by n matrix, and C is a scalar, then the scalar multiple of I and by C, by this constant C, is the m by n matrix C times A. And of course, as you can imagine, these the entries of this will be C times Aij. So this will be the matrix. Well, it's very simple. Well, let me point out a remark here, because in this way, since we can multiply a scalar by a matrix, I can also define the opposite matrix, so basically negative A. So the opposite matrix, negative A, is given by, so it's represented by -1 times A. So you multiply the scalar -1 by A. And for example, in this way, if A and B are of the same sizes of the same size, then we can also define, since I defined the opposite definitely, then we can define the subtraction. A minus B. And guess what? The subtraction will be nothing else than just A plus -1 times B. That's it. So that's the way you represent the subtraction. Or you can just subtract the two matrices and so on. All right, so let me give you a quick example, which is also in my notes at page 31 or 6, whatever you want to, depends on how you. So example, I'm going to give you an example of how we operate with matrices using both scalar multiplication and matrix subtraction. For example, let me consider the following matrices. The first one is, we'll consider 3 by 3. So the first matrix on the first row will have entries 1, 2, 4, then -3, 0, -1, 2, 1, 2. And B will be another 3 by 3 matrix. So this is a 3 by 3. Will be 2, 0, 0, 1, -4, 3, -1, 3, and 2. Okay. So I'm interested, well, in my notes, you'll see there are a bunch of operations, but I'm interested in computing. So compute 3 times A minus B, right? As you can see, this is an operation. So in the first matrix is a scalar multiplication, right? We have the scalar 3, which will be multiplied by the matrix A. And then in the second one, it's also a scalar multiplication. If you want to, you can represent it like this. 3 times A plus -1 times B. So you see, both of them, I'm adding two matrices right now. The first one, we multiply the first matrix by the scalar 3, and then with the second matrix, we multiply it by the scalar -1. So let's do this separately. So 3 times A, so that it will be easy. So this will be 3 times 1, 2, 4, -3, 0, -1, 2, 1, and 2. All right. So as I said, you multiply the scalar 3 by each element of the matrix. So this will be equal to 3, then we'll have 6 here, then we'll have 12, then we'll have -9, 0, -3, 6, 3, and 6. Okay, great. On the other hand, we will also have -1 times B. So I will multiply the scalar -1. So let me put it here, -1 times the matrix B. Matrix B is 2, 0, 0, 1, -4, 3, -1, 3, and 2. Okay. So this would be, so let's multiply it. -2, 0, 0. Then -1, 4, -3. Then 1, -3, -2. And now guess what? This implies that 3A plus -1 times B will be nothing else than just adding these two matrices. So the first one was 3, 6, 12. -9, 0, -3, 6, 3, 0, plus this matrix, -2, 0, 0, -1, 4, -3, 1, -3, and -2. Okay, And just like the usual addition, like we defined, this will give us something like -1, 2, 4, -4, 4, -4, and 3, -2, 0. Okay. So this is an example. So by now you can, and we will talk after I'm going to define the matrix multiplication. I will also talk about the algebra of matrices. You will see what kind of properties do these operations satisfy. This will be very, very important. Okay. So I think this is easy. Let me talk about now something a little bit more complicated, but not so. Since we talked about, okay, let me give you another definition. And this definition will involve, so definition. And this will involve the matrix multiplication. Okay. So again, if I have a matrix A, which will be Aij with the entries Aij. Here, Jose? Why is it -1? Where, the first here, you mean? Because I have 3 plus -2. It's 3 minus 2. Oh, it's 1. Sorry. You. Correct. Correct. A -1, it's 1. Yes, thank you. Correct. You're right. Okay, let me just do it because I just copied it like from my notes. So the first one is 1. This is 6. This is 12. This is -10. This is 4. This is -6. 7. 0. And the last one is 4. No, I think I copied the wrong because I'm looking also at the notes I want to see, and I was lazy of doing the computations. But anyway, I was copying the wrong matrix. Okay, yeah, that's great you pointed out. All right, so yeah, this is the correct version now. And I hope my notes is the same. Yeah, actually I was looking at the notes of A minus B. If we subtract A minus B, we'll get that matrix, not this one. So, yeah, correct. 7. Oh yeah, okay. I was looking at the wrong matrix. All right, so now let's define the matrix multiplication. So if I have a matrix A, so if this is an m by n matrix, that's good that you pointed out, because it would have been embarrassing if I would upload this video on my YouTube, and when people will look at it, it was like, look at this guy, he doesn't know how to add two matrices. You saved me. Anyway, so now, so if I have a n by n matrix, and let's say, and I have another matrix B with the entries B ij, right? And this will be, pay attention, this will be very, very important. This is an n by p matrix, right? And then the product AB is an n by p matrix. So now you can imagine under what conditions we can multiply two matrices, where AB will be these, will have these entries Cij, and pay attention here, where Cij, where these entries will be nothing else than just this, the sum from k equals 1 to n of a I k times b k j, right? This will be, as you can see, this will be nothing else if you want to write this. So this is how we um, define the elements of the product, the entries of the product matrix. As you will see, when I will do an example, you'll see that I take the first row and multiply with the elements from the first column. So this will be like a row column procedure. So this will be, if you want to write it, so this is AI1 times B1 J plus AI2 times B2J plus da-da-da plus all the way plus AIN times BNJ. Okay, so this is how we operate with the product of matrices. Okay, so now let me, so the definition means that we need to find the entry in the ith row and the jth column of the, and we need to multiply them. That's it. So for example, let me give you an example. Find the product of two matrices. So let me take the example from, it's in the notes as well. So -1, 3, 4, -2, 5, 0. And B will be, again, this is very important. This is what? How many rows do we have here? It's a 3 by 2 matrix, right? And so that we can make possible for this two matrices to be multiplied, we need to take a matrix that looks a little bit like this. Let's say -3, 2, -4, and 1. This will be a 2 by 2 matrix, right? So I can multiply them. As you can see, the multiplication will be possible because the number of columns in the first matrix coincides with the number of rows in the second matrix. Look here. All right, so let's do this. So AB will be equal to -1, 3, 4, -2, 5, 0. And this will be -3, 2, -4, 1. And now I'm going to ask you, okay, let me write again. 3, 2, and 2, 2. The result will be what kind of matrix? Can you tell me? What kind of matrix we will get here? Let's say
2 by 2.
What?
A 2 by 2.
Not 2 by 2.
3 by 2.
The 3 by 2. Right? You see here the number of rows is the same as number of columns, so it will be a 3 by 2 matrix. So I'll have 3 rows, 2 columns. So let's write them like this: C11, C12, C21, C22, C31, C32. And now the only thing we need to do is just to compute these numbers. So let me do a couple of them. So for example, C11. So C11 says the following. That's why I denoted it like this. It says multiply the elements from the first row from the first matrix with the elements from the first row, first column from the second matrix. So you'll have -1 times -3. Look here, I take this and I multiply by this, then I'll take the second element in the first row and I multiply with the second element in the first column, plus 3 times -4. And this will be whatever, it's -9. Now C12. C12, I'll take again the elements from the first row with the elements from the second column. So it will be -1 times 2. So as you can see, I'm doing it like this. And then the second one, I'll go a little bit like this. So -1 times 2 plus 3 times 1, which will give us 1. And then you keep going. Now you've done with the first row from the first matrix. Now you move to the second one. So C21. C21 says multiply elements from the first matrix, from the second row, from the first matrix with the first column from the second matrix. So we will have what? So we'll have 4 times -3 plus -2 times -4, which will give us -4. Again, C22, this will give us, again, I'm taking the second row and I multiply with the second column. So it will be 4 times 2 plus -2 times 1, which will give us 6. Right? Now, I'm done with this. Then I'm taking C31. So for C31, I'm taking the elements from the third row and I multiply again. So it will be, let's look at it, 5 times -3 plus 0 times -4, which will be -15. And then the last one, C32, it's 5 times 2 plus 0 times 1, which will be 10. And now finally we can write the matrix. So AB will be nothing else than just, so this will be a 3 by 2 matrix. So it will be -1 times -9, 1, -4, 6, -15, 10. That's it. This is how we multiply 2 matrices. Is it clear for everybody, the procedure? It's called row column procedure. So, but I want to make sure, because somebody said here, well, it was a little bit of a confusion. I want to make myself very clear. Remark. So when we multiply 2 matrices, let me show you how it's done. So I have let's suppose I have a matrix A, and this will be of size, is an m by n matrix. And I multiplied here by a matrix B, which is of size n by p. So these two are equal. They must be equal so that we can multiply the 2 matrices. And here, this is how the size, this is the size of AB, of the product. So this will give us AB, which is of size m by p. So make sure that when you multiply 2 matrices, make sure that the number of columns in the first matrix is the same with the number of rows in the second matrix, right? Anyway, and you can do it more generally. Now, I want to go back a bit to systems of linear equations. So let's go back to systems of linear equations. Yes, exactly. Yes, Cesar, it's correct. That's it. That is correct. Yep. That's the only way you can multiply 2 matrices. So systems of linear equations. So remember that we wrote a system of linear equations in the following way. So let me go back and write it the way we learned to write it. And I'm not gonna write it in its most general form. I'm just gonna do a 3 by 3. So it's A11x1 plus A12x2 plus A13x3 equals B1. A21x2 plus A22x, oh, sorry, x1 here. And it's a mistake in the notes. Or actually, oh yeah, A22x2 plus A23x3 equals B2, and A31x1 plus A32x2 plus A33x3 equals B3. So this is a system. Well, guess what? This is a system of linear equations. This can be written in its equivalent form now that we know what is a matrix multiplication. We can write this in the following way. So we can write this as a matrix equation. So the system can be written in a matrix equation form. And it will be written in the following way. Guess what? Very, very simple. This will be the matrix A11, A12, A13, A21, A22, A23, and the last row. And now we're going to multiply this by x1, x2, x3. And this will be equal to B1, B2, B3. Haha. Look at that. So this is the matrix A. This is, let's say, the vector times X. And this is another vector times B. Wow. So this is the matrix equation I'm talking about. And this can be written just like a system of linear equations. Now, let me give you a simple example. In fact, I will, before I go veering towards properties and talking about the algebra of matrices, because I want to talk about that. There are a lot of things I have to cover in this lecture, and we're gonna talk about this week about matrices, because we need to move on to something else as well. Time is very short. So let me give you a quick example. And example. Solve the matrix equation. So instead of saying that solve the system of linear equations, I could say simply solve the matrix equation AX equals O, equals the matrix 0, where A is this matrix 1, -2, 1, 2, 3, -2, and X will be nothing else than just X1, X2, X3. And of course, 0 will be just the 0 vectors 2 by 2. Okay, let's identify. Because you see, I'm making possible a multiplication here. Okay, first of all, I want you to tell me what is the size of A? What is the size of 2 by 3? So I have 2 rows, 3 columns. What is the size of X?
3 by 1.
3 by 1, correct. And the size of O, of the null matrix, is what? Is 2 by 1.
2 by 1.
As you can see here, the number of columns in the first matrix is the same with the number of rows in the second one. So it's possible. So instead of saying like solve the linear system of equations, I'm just telling you to solve this matrix equation. But no problem. Once you know the matrix multiplication, this will be nothing else. And I'll leave it to you for the details. When you multiply, this will be x1 minus 2x2 plus x3 equals 0. 2x1 plus 3x2 minus 2x3 equals 0. So I'm going to leave here the details to you. So make sure you check them out. So here I have a system of linear equations. Unfortunately, it's not a system the way we want it. We have 2 equations, 3 variables. So 2 equations and 3 variables. Anyway, by using, again, I'll leave the details to you, using the Gauss-Jordan elimination, details. You know how they say, I say details, but you know, there's a whole saying, the devil is in the details, so make sure you check them out. Okay, so by the Gauss-Jordan elimination, we obtain the following, so equivalent matrix. We obtain the following, the equivalent matrix, or the, you want to say the row echelon matrix, or row reduced echelon matrix if you want, which is given by 1, 0, negative 1 over 7, 0, 0, 1, negative 4 over 7, 0. And now when we obtain this kind of matrix, it's quite easy to observe the solutions, right? So let's see. Clearly, okay, first of all, by just looking at the system in the first place, what do you think? How many solutions do you think the system has? Okay, let me look at it here. Infinitely many, like Liliana said. So this will be like, so the system, so let me point out this S here. S has infinitely many solutions. Infinitely many solutions. Okay. All right, so since we have like infinitely many solutions, we can make a convenient choice of parameters. So we set up x3 to be 7t, where t is a real number. And then x1 will be t, then x2 will be 4t, x3 will be 7t. And then the solution, we can write a solution. We already have it here. So x1, so the solution is given by x1, x2, x3 will be nothing else than just t, 4t, and 7t with t real numbers. So these are the infinitely many solutions. So all of them will look like this. So they will depend on t, and you can plug in any value for t to get this. So I have here one question. Well, just look at it, right? If you look at the, so you have, this is x1 here, this is x3 here, this is x2 here, you see? This is the position for x1, this is for x3, and again, this is for x3, and this is for x2. So I can write x1 in terms of x3, right? Right? And I can write x2 in terms of x3. So definitely, maybe I should set up x3 to be, well, 7 times t, so that I can get rid of this 7 here, because it's 4 over 7. Because if I set up x3 to be 7, then I'll divide by 7 everything, and I don't want that. That's why. Is it clear now? Eduardo? Okay, let's write it again. So you see, when we write this in row echelon form, we have here, what do we have? We have x1 plus -1/7 times x3 equals 0, right? And from the second one, we can infer that x2 plus -4/7 times x3 equals 0. Or if you want, x1 is x3/7, or if you want, x2 is 4x3/7. So I say, let's put here x3 to be 7t, so that I can simplify by t. So if I put here x3 to be 7t, right? I'll have what? I'll have x1 to be 7t/7, which is t. Then x2 will be 7t/7, which will be 4t. And then this is how you get the solutions here. Okay, I hope that's clear now. Okay, perfect. Just for a refresher, I would suggest you go back to the first, go back to the previous lecture. Okay, so now this has infinitely many solutions, and probably as you have been used in the, okay, let's write them in the column form. So like this, x1, x is x1, x2, x3, because I believe you have something similar in the online homework. So this will be equal to t, 4t, 7t. And we can factor t out because it's a scalar, so t is, so it's t times 1, 4, and 7, with t real. So in other words, all the solutions are, this system has infinitely many solutions, and all the solutions are spanned by this vector right here. Anyway, now let's talk about the algebra of matrices. And here we will see properties, and the first one we'll talk about the properties of addition, and scalar multiplication. So that's the first thing I want to cover. So let me, if I have three matrices, A, B, C, are m by n matrices. I'm not considering square matrices, just m by n, and C and D are scalars. Then the following properties hold true. Okay, so now, as you can expect, let me write this with red. First one, A plus B is nothing else than B plus A. So the point is that the addition of two matrices is what we call commutative. Okay, that's a good thing, because for matrix multiplication, so this is commutativity. Because for matrix multiplication, this will not necessarily hold true. The second one is associativity, which is a great thing. So A plus B plus C is nothing else than A plus B plus C. So this is what we call associativity. Okay. Then the third property is, like, if we multiply two scalars, let's say C and D, two real numbers, by a matrix A, is nothing else than just multiplying the second one or the first one by the matrix A. So this is the associativity, but it's not the associativity of matrices, it's the associativity of scalar multiplication. Now the fourth one, if we multiply the scalar 1 by A, is nothing else than just A. So this is just the identity, the scalar identity, multiplication by the scalar identity. The fifth one is if I have something like this, I have a scalar and I multiply by the addition of two matrices is nothing else than just multiply the scalar by each matrix and we add them up. So it's called, what we call this is distributivity. With scalars. We will see that something similar will hold true when we, or if you want something similar, C plus D times A is C times A plus D times A. Again, it's the same thing, distributivity. All right, so these are the properties of the matrix addition and scalar multiplication. So basically you can do almost everything you want, but not that much. Now, let me give you another, let's discuss about some other properties. For example, properties of zero matrices. And here, I'll consider, so if A is an m by n matrix, and C is a scalar, then the following properties are true. Hold true. And the first one is A plus the zero matrix is nothing else than just A. So if you add A by the matrix whose elements are just, whose entries are just zero, then you get the matrix A. The second one, if we add A by the opposite A, and we have seen what that means, is just multiplying the opposite of the matrix is just multiplying negative, the scalar -1 by the matrix. So this will give us nothing else than just the null matrix, right? So this is what we call, this is the null matrix or the zero matrix. The third property is the following. If a scalar times a matrix is the null matrix, this is a very important property, then C equals 0, then the scalar is 0, or the matrix itself is 0. So, or A is 0 mn. Oh. Right? So these are the properties. Well, you can, there are some examples, but I don't want to lose too much time with it. At page 14 in my notes, how you can operate with this. I want to talk about, so I want to dwell more on the most important and a little bit more difficult things. And now I want to talk about, since we talked about the properties of matrix addition and scalar multiplication, I want to talk about, yeah, I want to talk about properties of matrix multiplication. Of matrix multiplication. Well, here it's a little bit, we have to be a little bit more careful, but you'll see that something amazing will happen with the matrix multiplication. I think I have already told you at the beginning. Well, anyway, we'll see them again now. So if A, B, and C are matrices, and here with sizes such with sizes that the matrix products are defined, that the matrix products are defined, right? So if I have these three matrices, we have already seen under what conditions we can define the product of two matrices, and C is a scalar. Then the following properties hold true. So we have the following properties. The first one is, it's an amazing one. A times BC is nothing else than AB times C. So this is what we call associativity. This holds true for any three matrices. This is an amazing property. Okay, then the second one, what if we have some kind of distributivity? A times B plus C will be nothing else than just AB plus AC. So this is distributivity. The third one, of course, we can, this is, you see, I multiply by the matrix A to the left. Now, what if I multiply, what if we have something A plus B times C, everything times C, so I'm multiplying by the matrix C to the right. So again, it will be AC plus BC. Again, this is also distributivity. So the first one we can call it distributivity to the left, and this will be distributivity to the right. So pay attention here. This is, no, C is not a scalar, C is a matrix. This is a big C. Matrix. Look, this is a big C, and this is a little c. You see the difference between them? This is matrix, this is scalar. All right, so this is distributivities, and both of here imply matrices. And now the fourth one, which will imply the scalar, so it will have C times AB, and this is a scalar here. This is nothing else than just C times A. I multiply by the first matrix, and then I multiply by the second matrix. Or if you want, this will be nothing else than A times CB. It doesn't matter. Okay. So these are the properties of the matrix multiplication. Okay. Now I'm gonna give you something. Oh my God, there's so much to do. I'm gonna give you something. So remark. The matrix multiplication is not commutative, not necessarily commutative. So in other words, the AB is not equal to BA necessarily. You can find two matrices for each two all the time. You can find two matrices for which they can such that they commute, but you can also find two matrices so that they don't commute. And the example, let me give you the quick example that I have here in mind, is the following. So let me take these matrices. The first one, A, is 1, 3, 2, -1, and B is 2, -1, 0, 2. Well, if you compute AB and BA, so AB will be, okay, let me write it, 1, 3, 2, -1 times 2, -1, 0, 2. And when you multiply, this will give us 2, 5, 4, -4. And BA, so I'm multiplying the other way around, so I'm putting B first, 2, -1, 0, 2, then 1, 3, 2, -1, and this will be 0, 7, 4, -2. As you can see, they don't look quite the same. So AB is different than BA. Okay, you know, you can look in my notes to see some other examples of this type. So now I want to talk about some special type of matrix, another special matrix, square matrix. Let me look at this, the identity matrix. Because with the identity matrix, this will be nothing else than just we have 1, 1, 1 on the main diagonal, and the rest is 0. Or if you want to write it, 1, 0, 0, 0, 1, 0, all the way 0, 0, 1. So this means that on the main diagonal, the elements are equal to 1. So this is what we call the main diagonal. The elements on the main diagonal are 1, or equal to 1. That's what it means for the matrix to be an identity. So for example, for n equals 1, we have I1 is just the element 1, which is basically a scalar. For n equals 2, we have I2 is, so it's a 2 by 2 matrix, 0, 1, 1, 0, sorry, 0, 1. For n equals 3, you will have the identity. We'll have it like this, 1, 0, 0, 0, 1, 0, 0, 0, 1. So that's the matrix. And why is this the identity important? Because when you multiply, so very important fact, and it's stated as a theorem, if A is an m by n matrix, then we have the following. A times the identity is A, and the identity times A is A. So it doesn't matter how you multiply it. You multiply it to the left, you multiply it to the right, it will give you the same thing. So that is the only case when you have commutativity with the identity. When you have the matrix with the identity, you always have commutativity. Also, I want to mention something. When you raise, another thing is when you raise a matrix A to the power K, this is nothing else than just A times all the way times A, K times. So you multiply A by itself, K times. So for example, if you take the matrix, let's say, so example, if you take the matrix A to be 2, -1, 3, 0. And you want to find a squared. This is nothing else than just 2, -1, 3, 0. You multiply it by itself, 2, -1, 3, 0. And this will give us what? If 1, -2, 6, and -3. And then you keep going. If you want to find a cubed, you multiply a. So a cubed, for example, is nothing else than just a squared times a. And you keep going. 1, -2, 6, -3, and you multiply by a, which is 2, -1, 3, and 0. Anyway, I'll leave this computation to you. It's not a hard thing to do. All right, now another matrix I want to talk about, it's the transpose of a matrix. Of a matrix. The transpose of a matrix, so if I have a matrix A, which will look a little bit like this, let me write it explicitly. A11, A12, A1n, A21, A22, A2n, all the way, going all the way AM1, AM2, AMN, right? Then this is a size m by n matrix. Then the A transpose, guess what? I'm just going to reverse. I'm going to take the rows, I'm going to transform them into columns. So A transpose, so this is the transpose of A, right? So this is the transpose of A. The A transpose will be nothing else than just the following. I'm going to take the first row, so A11, A12, A1n, then A21, A22, A2n, and you can see that I'm writing those columns. M1, AM2, AMN. As you can see, the main diagonal will stay the same. So this will be of size n by m. And now let's see some properties of the transpose. So properties. No. Do you see that? Look, it's a m by n. It's not a square matrix. So properties of the transpose. Of a matrix. So the properties are the following. So if A and B are matrices, with sizes such that the matrix operations are defined. And C is a scalar, then the properties below are true. Okay, so the following properties are true. The first one is if we transpose twice, we go back to the initial matrix. So this is what we call the transpose of A transpose. The second property if I add two matrices and then I transpose them, this will be easy. It's just by transposing each matrix. So this, and you add them up. So this is a transpose of a sum. Then we'll have C times a matrix, or scalar times a matrix transpose. This is nothing else than just multiplying the scalar by the transpose. So the transpose of a scalar multiple. The fourth one, which is very important, and I'm gonna write this in a different color. What color should I pick? Okay, green. AB transpose is not as you might imagine. This is nothing else than just B transpose times A transpose. This is the transpose of a product of a product. Okay, so these are the properties of the transpose. And there are a bunch of examples, but probably I'm gonna do a follow-up for this. Anyway, we'll see, because I didn't manage to finish everything, so I'm gonna do another video. But probably I will not require you to be to attend that. Probably I'm gonna do it on my own, but anyway, we'll see. So let me give an example of two matrices. For example, how to find, so finding the transpose of a product of a product. And the example that I have in mind right now is the following. So in other words, let me consider these matrices. A to be 2, 1, -2, -1, 0, 3, 0, -2, 1, and B to be 3, 1, 2, -1, 3, and 0. Okay, so the first matrix is clearly a square matrix, a 3 by 3, and the second one is what? Is what? What kind of matrix is this? What is the size?
3 by 2.
So how many rows do we have here? 3 rows, right? And 2 columns, 3 by 2. So the product, which you should expect to be something like 3 by 2, right? But anyway, let's multiply them. When we multiply these two matrices, so let's write them here. 2, 1, -2, -1, 0, 3, 0, -2, 1. Multiply by 3, 1, 2, -1, 3, 0. So the result will give us a 3 by 2. So this will be 2, 1, 6, -1. And we'll have -1, 2. Again, this is a 3 by 2. Okay, you can transpose this. So when you have the product, the 3 by 2, when you transpose this, it will be a 2 by 3. Right? So AB transpose will be 2, 6, -1, 1, -1, and 2. Right? So this is a 2 by 3. And now, if you want to compute by yourself, and when we compute B transpose times A transpose, we will have, when we transpose each one of them, so we'll have 3, 2, 3, 1, -1, 0. And we multiply this by A transpose, which will be 2, negative 1, 0, 1, 0, negative 2, negative 2, 3, 1. And by doing the computations here, when you multiply this, guess what? You'll get exactly the same thing. 2, 6, negative 1, 1, negative 1, and 2. So again, this property was verified. So AB transposed is nothing else than just B transpose times A transpose. So that's it. Well, there also, I think I'm going to stop here for today. Unfortunately, I didn't manage to finish all the lectures, so I've done half of it. It's kind of ridiculous for me to do 52 pages. So what I'm going to do will be the following. There will be a follow-up lecture for this. I will record it. I'll record the follow-up. So um, by myself, I'll do it. I will not require you to attend. In fact, I'm not requiring you anyway, so it's only optional. And then you'll receive probably two separate videos for this week. Okay, I'm gonna stop here.